Hi, good afternoon, and welcome to this talk about board support packages for Yocto Project. So, first of all, how many of you are users of Yocto Project at the moment? Some. Okay. Anybody maintaining a BSP here for Yocto? One, maybe. Cool. Okay. So first of all, a little bit about myself. So I'm Chris Simmonds. I've been doing stuff with embedded Linux since 1999. I've written a book on the subject. It's a good book, just saying. And you can contact me by electronic means by these various channels. However, so this talk then is going to be about board support packages and Yocto. So in Yocto, the board support package is written as a meta layer, and I'll explain what that is later on for those of you who are not Yocto regular users. So every project needs a BSP because the BSP defines the hardware. Okay, you pretty much can't do anything without a BSP of some kind. So where do you get the BSP from? The BSP either comes from the guy who sold you the board, which could be a Raspberry Pi, for example, or it could be a commercial board from one of the many companies that make embedded boards. Or if you are that guy who provides the board, then you're going to have to write the BSP yourself. Or if you're developing in-house hardware, then somebody's going to have to produce the BSP for that board. Either way, the BSP is the foundation of the stack of layers you need to make the software work. So the BSP is, I believe, the most important part of the whole thing. So this is all about how to write a BSP, what is good, what is bad, about what goes into BSP layers. But before we get into that, I want to do a bit of a prefix, talk a little bit about Yocto, what Yocto is, and how the various bits put together. So in particular, I want to give you the terminology. So when we talk about layers and recipes and bbappends, we all know what those things really mean. So Yocto Project, there's the URL. So Yocto Project is a build system that creates a Linux distro for you. With Yocto, you feed in a configuration and a bunch of recipes, and then it magically munges that all together and produces, first of all, binary packages in some format, usually RPM, but it doesn't really matter. And then it combines those binary packages into images, and then you flash those images into the flash memory of your target device, or put them onto an SD card, or whatever it is your device supports. So Yocto, and Open Embedded. I should mention Open Embedded here because just in case any of the Open Embedded guys are watching this. So Yocto Project and Open Embedded are kind of the same, but also somewhat different. Open Embedded actually was the start of all this. 2003, Open Embedded was started. Yocto Project is kind of a fork of that, which came along in 2010 for complicated reasons, which I'm not going to go into now. But Yocto and Open Embedded are kind of the same thing, but also different. Let's just leave it. Yeah. Well, okay. So why do you want to do this? Why don't we just take Debian or distro of your choice? And the reason is that if you do take Debian, as you do with the Raspberry Pi, with Raspberry or now Raspberry Pi OS, as it's now called, the problem with a full-blown desktop distro is it brings on board a whole bunch of stuff you don't really want. It's difficult to split Debian up into small enough pieces for a really good embedded deployment. You end up with a bunch of stuff you don't need. You end up with more attack surface than you really need. You end up with maintenance problems and so on. So in the general case, Debian is not a good choice for an embedded operating system for those reasons. So let's talk about Yocto. So Yocto has a 6-month release cycle. We're currently at 3.3 with the codename Hardknot, but it will soon, in the next couple of weeks, be superseded by 3.4, which is just about to be released, and that has the codename Hollister. And you can see the previous versions as well. Every now and again, there is a long-term support release. So the LTS release is 3.1, which is Dunfell, which actually is from April last year. So how do you get Yocto? Well, you go to this Git repository, and you do a git clone, and -b in whichever branch you want, or if you want the main branch, leave out the -b bit. That will download for you a total of about 250 megabytes, of which 55 megabytes is the actual metadata. Okay, so not so much. Why so small? That's because what you've downloaded is just the metadata, the recipes. You don't download the code at this point. It's only when you do the build that it downloads the code for the packages that you want. So after you've done the git clone, it will, by default, clone into a directory called Pocky. Again, there's reasons why it's called Pocky, which I really don't go into just now. It just is. And then within that directory, you will find there's a script called OE init build env, OE for open embedded. So you need to source that script in order to set up various shell variables. And that will create for you a build directory if it doesn't exist already. You can give the name of the directory you want it to create here as a parameter. If you don't give a parameter there, by default it's called build. And then within that build directory, there is a configuration directory called conf. And there's a bunch of configuration files in there. The main one is called local.conf. And it's within the local.conf you set up what it is you want to build. So you have to go and edit this with a text editor. Typically, you'll put things in here like machine equals something or other. So if I'm building for a BeagleBone, I specify BeagleBone. If I'm building for a Raspberry Pi, I put Raspberry Pi. So that actually is the board support package. So this is the bit we're going to be talking about, is what do we mean by BeagleBone or Raspberry Pi? What does that point to? You can also select the distribution. The default one is called Pocky. And the distribution is basically the policy of which components you want to download and install. So do you want the latest of everything, or do you want to have a conservative approach to the packages you install? Which NetDaemon do you want to use? Which graphics environment do you want to use, and so on. So the distro is policy. When we've got a choice of packages, which one should we install? Package class, this allows you to specify the intermediate packaging format. The default is RPM, and to be honest, there's no good reason to ever change that. So we kind of leave that. And then there are various other things, including extra image features. It's documented. I'm not going to go into details here. But this pretty much does what it says. It allows you to add additional things in. So for example, a good one to do when you're developing stuff is add in debug tweaks. That will add in GDB and I can't remember, a few other useful debug tools. So the core of the Yocto project metadata are called recipes. So we have recipes. These recipes are gathered together into layers. And then there's a tool called BitBake, which is the task scheduler, which processes the recipes and will perform whatever instructions are needed. So BitBake will generate binary packages in RPM format by default. And then as a final step, when it generates the image, it will take the RPM files and unpack them to create images. And then those images are flashed into your flash memory. So just as a random example then, this is what a recipe looks like. This is the canonical Hello World recipe. What can I say? So the first bit is just fluff. We can ignore the first three things, in actual fact. Oh no, sorry, the first two things. The third thing is the license. The license is important. Every recipe must have a license. Okay, we believe in licenses. Licenses are very important. Not only must you say that it's an MIT license, you must also give a pointer to the file or a file that contains the text of that license. And we also have an MD5 hash of that file just to make sure that nobody has gone and changed the license when you weren't looking. So licenses are important. Next bit down here, we have a line that says source URI. So this is a list of places to get the source code for the component that you're going to compile. Usually in source URI, this will point to a tar file on some server somewhere. So you'll have source URI is https:// some URL / some tar file. Or you could be a Git repository. So you'd have git :/ and then a Git repo. But in this case, because this is a simple Hello World program, we are just using the local MIME type file : / so that is a local file actually packaged as part of the recipe. Then we have instructions to compile this thing. So do compile, that's the instruction that BitBake uses to compile stuff. And so in here, we specify how we build this thing. This is a simple CC, so we're just going to run the compiler. We're going to compile hello world.c, and we're going to generate a binary called hello world. Usually you'd have a makefile here or something, but this is simple. And then there's a do install section which says, having built hello world, where do you put it? So we want to put it into something called bindir. Bindir turns out to be user/bin. So this is going to install it into, this is going to do an install -m hello world, and it goes into bindir. So we'll end up with user bin hello world. There are other things for other useful places as well as bindir, like libraries and such like, which I think is called libdir. Okay, so that's roughly speaking what a recipe looks like. Yeah, you get the basic idea now, I hope. So in Open Embedded Yocto Project, we have, first of all, we have the configuration file I just mentioned. So in build/conf, you have this local.conf file, which specifies your machine and your distro. And there's another file called bblayers.conf. So that is the list of layers in your project. And for example, we have here a couple of layers. So a layer is just a directory which contains BB files. By some convention, the layers are prefixed with meta. So we have meta this and meta that. The most meta one of them all is just called meta. So that's the really basic stuff. And then meta Pocky is the recipes for the Pocky distro. And we'll see in a moment or two, your board support package will be its own meta layer. And then within the layers, so these are just directories, and they just contain a whole bunch of BB files and a few other things which we'll come to in a moment. Now, the idea of layers is really powerful because it means that we can just build up our project by adding in layers for whatever it is we want to do. So you'll always start off with the meta layer because that's always required. You'll need a distro layer, for example, meta-pocky. You'll need a BSP layer, but there are hundreds and hundreds of other layers you can just add in as you need them. Oh, okay. Just for reference, this is what the bblayers.conf file looks like. Well, it's a list of directories. It's not complicated. Okay, so that's the basic structure of Yocto Project. So now let's look at the layers, and in particular board support package layers. So there's what I call the trinity, the holy trinity of Open Embedded and Yocto Project. Distro, machine, image. So the distro is how I want to build my system. That's the policy, which versions of packages do I want to use, that kind of thing. So high-level stuff. The machine, this variable is the board. In other words, the board support package I want to use. And then the image is the image recipe I will use when I build the target images. Now, the neat thing about this is you can swap any of these things around, and it should, in theory at least, still work. So say I have several boards that I'm producing. They could be different architectures. One could be ARM, one could be x86, one could be RISC-V. Yes, RISC-V is popular these days. So long as you have a board support package for each of those, you can just specify the machine here, leave the distro and the image the same, and you'll get the same thing built for these different architectures. Or in a similar way, you can just change the image. So we can have one image that is just bare metal. We can have another image which has a graphical environment. We can have another image that's for pre-production tests or whatever. So we keep the distro and this machine the same. We just change the image for whatever it is we want to do with that particular board. So it becomes very powerful and modular, which is quite neat. So layers. So there are 3 types of layer: BSP, distro, and everything else. The BSP layers then, they define a machine variable. So the way you know it's a BSP layer is it has this file here in conf/machine/something.conf. And where I put machine in brackets, that just is the name of the board, which could be Raspberry Pi or BeagleBone or whatever. Distro layers, you can tell it's a distro layer because it has a directory called distro and a conf file in there. If it has neither, then it is an everything else. So these are often just called software layers. So this is stuff that is not distro or board specific. So libraries, Qt, Qt5, meta-Qt5 is a layer, for example. Languages, there's a meta-Java layer. Virtualization, SE Linux, there's a meta-SE Linux. Actually, meta-security is for SE Linux, and so on. And there is, I don't think I've got it on the slide, but there is a website you can go to called Open Embedded Layer Index. Layer Index Open Embedded. Can't quite remember, but Google it. Which lists out 300 or 400 of layers like this. Plus there are private layers that you will get, you will find links to from various places. So like I said, the layer concept is really, really powerful. Yes, it may have occurred to you in my description of that, there is a 4th option. You can have a layer which has both a machine and a distro configuration. We do not talk about these. They should not exist. They do exist, but really they shouldn't. So if you find you have a layer which has both of these things, yeah, something somewhere has gone wrong, and you really need to refactor it. Okay, so So let's talk about BSPs. And what I want to do from now to the end of the presentation is to go through some of the things, not everything because we don't have that much time, but some of the things you'll find that are specific to BSP layers. And I want to kind of point to the best practice when you're laying out the BSP. Or conversely, even if you're not writing the BSP, I want you to recognize a good BSP when you see one. And that's just as important. So first rule of BSP layers, keep it simple. And this is probably the biggest problem. Quite often, there is too much stuff put into the BSP layer. The BSP layer should have the machine configuration file. So that's the thing in conf/machine/whatever.conf. And it should have configuration for your bootloader, whatever that might be, the kernel version you want to use, and any modules that requires. Maybe some firmware binaries that you need to boot the system up for various bits and pieces. Other hardware-related stuff, so maybe GStreamer libraries for the particular video controller you have, that kind of thing. And nothing else. So it should only contain hardware-specific stuff. There should not be any generic stuff in here at all. That belongs in a different layer. And meta-raspberry Pi actually is a good example. If you are building a BSP, go see what meta-raspberry Pi have done. That's a very good template. So yeah, I'll kind of step through a couple of things. So supposing I am producing a range of boards called Nova. They're called Nova because they're new, they're sparkling, and also they explode for no well-understood reason from time to time. We're working on that. So I go BitBake layers, create layer, MetaNova is a good name for it. So all that does actually is create a directory. So that creates me a directory called MetaNova with a couple of subdirectories in it. And then I need to add that layer, so I type BitBake layers, add layer, MetaNova. It's now part of my bblayers.conf file, and any recipes I create in that MetaNova directory will be part of my project. It will generate for you, when you do the create layer, it will generate a template README file. It's good practice to actually put something sensible into that README file to explain what the layer is for, which boards do you support, any other interesting stuff to anybody using this layer. And a license. Everything has to have a license, including the layer metadata. Most people choose an MIT license for the layer metadata, but of course you can choose whichever license you like. And then you would want to create the configuration files for your hardware. So in conf/machine within MetaNova, we will create two files because we have the Nova and the Nova Pro, which we're very proud of. So we have two configuration files, one for the two boards, because they're sufficiently different that a single configuration wouldn't cover them both. And then when I do a build, of course, I select which machine I'm using by putting into my local.conf file machine equals Nova Pro, for example. Then we start populating the nova.conf file. Probably one of the places I want to start is the bootloader. How do I boot my board? Most likely I'm using uboot. So I put extra image depends plus equals uboot. Pretty much job done. So this variable here, extra image depends, is a list of packages that need to be built, but not included in the final root file system because the bootloader is separate from that. it's quite likely that I will need to configure U-boot for my Nova board. And the way you would do that is through something called a bbappend. So I will create also in my metanova, I'll create a U-boot, some version, bbappend, and there I'll put in the stuff that's specific to my configuration of U-boot. So that may contain some additional configuration files for U-boot, may contain some patches to add some drivers or something for my board, whatever. And I've chosen a version number, so 2021-01. So let's talk a little bit then, as a digression, what about these version numbers? So every recipe has a version number. So with U-boot, U-boot is the name of the package, and then the version number is usually expressed like this, with an underscore, and then whatever the version number string is. And it's expressed as part of the recipe file name. There are other ways of doing it, but this is the most common way of doing it. When BitBake processes package U-boot, so back here I didn't specify a version, I just said I want U-boot. So BitBake will simply go and use the latest version of U-boot it can find. Oops. If I want a specific version, and if that version exists as a recipe somewhere, I can put preferred version underscore name of package, say 2020-11. We can also use wildcards here. So when it comes to the Linux version can have 3 separate digit fields. So we can put a % here, that's the wildcard, and that will match 5.4.1 and 5.4.2 and 5.4.3, etc. Okay, digression number 2, I mentioned bbappends just now. So let's elaborate on that a bit. So the bbappend mechanism within Open Embedded is really, really powerful. It allows us to modify an existing recipe without actually changing the text of that actual recipe. It's pretty simple. I simply need to create so I have U-boot, some version number. But for my Nova board, I need to add some stuff in there specific to the configuration for my board. So I create a file in my layer called same name, same version, .bbappend. And then in that bbappend file, I put my additional stuff. When it comes to parse that, it literally takes the base BB file and literally appends whatever's in the bbappend to the end of it. And then it parses that. So this allows me to, in the bbappend, to override things that are defined in the BB file, if I so wish. Or I can add new stuff. I can even remove stuff if I really want to, although that's problematic. And again, we can use wildcards. So if I want my bbappend to apply to any version of U-boot, not just this particular version, I can put a % in there. Okay. Next thing I probably want to worry about is what kernel am I going to be using on my board. So I specify this again in the machine.conf file. So nova.conf, for example. I put preferred provider virtual kernel. So I haven't spoken about this too much, but you have these virtual packages called virtual/something. One of them is virtual kernel. And you assign to the virtual package the actual package you want to fulfill that role. So virtual kernel is going to be Linux Nova. So that is a specific version of Linux for my Nova board. And so preferred provider, I can also give a version number. So maybe there are several versions of Linux Nova, and I specifically want the 5.10 version. Notice that I'm using a question mark equals for the assignment here, because somebody can override that with a BSP in a higher level layer. So somebody may come along and use my BSP, say, well, BSP is great, but we really want to use 5.14 or whatever the latest version might be at the time. So BitBake assignments, we have two forms of regular assignment, lazy and immediate. If you're familiar with make files, this is similar to how GNU Make works. So the lazy assignment, it only actually does the assignment when it parses when it dereferences the variable with the equals in it. This can be problematic because it does mean that if you dereference the same thing in different places, they can actually turn up with different values sometimes. So I generally recommend people not to use the simple equals. Colon equals is more deterministic. This does an immediate assignment when it parses that line, and once it's been assigned, it's never going to change. Usually that's the behavior that you want. And then we have the conditional assignment. So question mark equals means we only do the assignment if it's not assigned already. And then there's also the double question mark equals, which is, no, it isn't. This is this is the default. So essentially what it really means is that once we finish parsing all of the scripts, we then actually go through with a final pass, and in that final pass, we do the double question mark equals. So a question mark equals overrides a double question mark equals, essentially. No, there isn't a triple question mark equals yet. I'm sure it's in the planning, but we haven't got that far yet. So anyway, so when we're doing assignments in the BSP layer, which is one of the lower level layers, it's good to use question mark equals because someone can come along with a bbappend and override that with a colon equals with a different value, and then we'll just pick that up when this gets processed. Step back to the slide here before I did the digressions. There we go. So in this case, then, I'm going to use my own special kernel, which I've called Linux Nova. So this presumably is something that I have cloned from kernel.org, and then I've got my own special tree. This is not the recommended way of doing it, by the way, but it does happen sometimes. For example, with Raspberry Pi, the Raspberry Pi kernel is not the mainline kernel. You have to go and get it from raspberrypi.org. So I mentioned, I've documented this because it's kind of the simpler concept. So how do we do this? I would need a recipe called Linux Nova and then some version number, and that would then have the necessary instructions to do a git clone from my own nova.com git repository or whatever. If, on the other hand, you're using one of the standard kernels, so there is a standard kernel called Linux Yocto. I should really flip this around because that's actually the recommended way of doing it these days. Then I would use, I still want to make some changes, but I can do that with a bbappend on Linux Yocto, whichever version. Next, let's talk about device trees. This is almost certain that you will need to modify this. So the device tree determines which bits of hardware are active, alive, and you need to, if you want to remap your GPIOs to do certain things, you do that in the device tree. So this is one of the things you almost always need to change. There are various ways of doing this. Again, I'm taking the simplest case where we're simply going to replace the device tree with a new one. So we have a device tree for the Nova board called Nova DTS. So it's in my kernel recipe in Linux Nova DTS. So that's the source for the device tree. And then I need to tell the kernel build recipe which device trees to actually build at build time. So I do that with kernel device tree equals, or colon equals, and then one, or actually several device trees if I so wished. It's up to you. And that will then generate for me a nova.dtb, and then later on I would have to do some scripts or whatever to tell the bootloader, uboot, to load nova DTB at boot time. Firmware, yeah. So firmware is a real pain, to be honest. So by firmware, I mean the various binary blobs that you need to program into various bits of the system to make them work. The example here is from the Raspberry Pi, actually. The Wi-Fi, yes, this is the Wi-Fi chip. I'm talking about, it probably does Bluetooth as well, I'm not quite sure. Anyhow, to make this chip work, you need to load this binary into it at boot time. We don't need to do anything with that binary. We just need to load that binary into the appropriate location, whatever it is, and away we go. So for this to happen, we need a recipe called Linux firmware RPi distro something BB. But we also need to tell the build system that we need to build this recipe, which will include the binary, and then load it at boot time, So we do this with machine extra R recommends, and then the name of that recipe. That will load the firmware for this chip. When we boot up, the Wi-Fi will work. How are we doing? Yeah, not too bad. What else? Right. Okay, so there are many other things I can mention of bits and pieces you could include into the BSP. But I think you're getting the view, the general feel of how you do this now. So next thing I want to look at then is the image format. So the whole point of doing all this is to create images. And you need to determine what format of those images you want. So Yocto has image builders for various things. The simplest is tar files. So that's just a tar gz file. More sophisticated things is we can create partition images. So these can be in a regular file format, such as ext4, or they could be probably not JFFS2, but it might be UB, a flash file system format to program into NAND flash memory. Or we can create a disk image. And with a disk image, that includes a partition table, maybe a boot block, and you can just flash that into eMMC or something like that, or an SD card. So these days, probably the last one, the disk image, is the most useful one, because most devices these days come with either SD cards to boot from or eMMC, and eMMC is just a SD card with legs on that you solder onto the board. So you select which file formats you want. In your machine.conf file, you put image fs types equals, and you can give a list. So in this case, I've chosen ext3, which is a rather weird choice. I can't remember why I put that there, actually. ext4 would be more likely. Or tar bz2. Well, why not? If I want to create a partitioned device that I can put into onto an SD card, then I can use a thing called WIC to do that for me. Funny story about WIC. WIC actually stands for the Open Embedded Image Creator, or OEIC. And then somebody realized, or became apparent, that you cannot possibly pronounce OEIC, not in English anyhow, OIC. So OIC became WIC. So that's why it's called WIC. The W doesn't stand for anything. So, so you end up with a WIC file, and you put it typically into a directory called WIC in your layer, so in Metanova in our case. There is, for historical reasons, there's also another directory you can put them in, but that would be a bit crazy. So if we want to generate a WIC file, we just add WIC to the list of types. And then we create a WKS file, and we reference it like this. So, this is for BeagleBone. So we have BeagleBone Yocto WKS that contains the instructions to format the image, ready to put into in the case of BeagleBone, the eMMC that's on the BeagleBone board. I don't think, yeah, okay. I didn't include the stuff about the format of WIC. It's a little bit convoluted, and I didn't want to go into too much detail there. But yeah, you can look it up now. Now you know what it's called, you can look it up. Okay, so first of all, the BSPs, keep it simple, but obviously it's not that simple because it's a complicated thing you're doing. So keep it as simple as possible. The second rule of BSPs then is don't break things. And this is where the things tend to go wrong. Yeah, so let me go through some of the pitfalls and some of the things you should look out for. The first issue then is that the person creating the BSP layer in some well-known company or other probably isn't thinking about products you may be using from, for example, competitors. They will assume you're always going to use their product and never going to use any other product. That is not the case, of course. So one of the issues is that quite often BSP layers are written in such a way that they destroy everything else. So long as you're using that particular board, fine. But if you want, if you have a if you have a Yocto set up with multiple BSPs and you just want to select the BSP by setting the machine, then you'll find that there is stuff in some BSP layers which basically destroy other BSP layers. This is not friendly. So if you are creating a BSP layer or if you're testing, it's worthwhile just seeing what happens if you add that BSP layer in your bblayers.conf file, but don't use it, actually select a different machine. It should still build. That's logically consistent, but quite often it doesn't. And usually the problem is with these bbappends. If you have a BSP layer with a whole bunch of bbappends, which then interfere with other recipes that you may be using in other layers, yeah, the whole thing blows up. So, okay, right, I've just said that. Another problem is dependencies. So quite often one layer depends on other layers. And so when you're doing running the BitBake build, BitBake whatever, you get errors like this. Could not include required recipes, blah, blah, blah. Essentially, the problem is then that Linux IMX is in a different layer and we don't have that layer. So then we have to go and scratch our heads a little bit, work out where Linux IMX is coming from, include that layer. It would be nice to avoid that. And it's very easy to avoid. you just need to put into the layer.conf file your dependencies. So we depend on core and freescale layer, and it turns out freescale layer is the one that contains Linux imx.inc. So be nice, get your dependencies right. Check your layer. So there's a really handy little script called Yocto check layer. And it's got various heuristics and tests built into it, which will validate that your layer is at least halfway sane. So it's a good way to do this. So it's a good thing to do this. You just run the command pointed at your layer, and it chugs through. In this case, it says this is a BSP layer. It knows that because it's found a machine.conf file. And then it does various things, and hopefully you want to see at the end, pass. There you go. There's a gold star for you. The final thing, and this is really the biggest bugbear I have with BSP layers from many sources. When a company, so this typically happens when you buy an off-the-shelf single board computer or system on module from one of the many companies. The marketing department of the company often see the BSP layer as being the showcase for their product. And so they will load, as well as the BSP stuff, they will load in demos, splash screens with their company logo in, all kinds of stuff which you really don't want and don't care about. So the BSP layer is not a marketing tool. The BSP layer is just there to make it work. If you want to have demos, fine, great, I like demos, but put them into a separate layer. So I can include the demo initially, just to see all the fine things you do, but when I produce my thing, I want to do it my way, not with your funny splash screens and demos. Another thing then, which kind of relates back to this thing here. So quite often when you are using a BSP with a whole bunch of stuff, there are multiple layers. And it's, even though you put the layers here, so at least it will tell you that a layer is missing, it's even nicer if you can actually load all the layers in one go. So one common way to do this actually is to use repo. So repo is from Android, but it's basically just a wrapper around Git. You give it a manifest file, which is an XML file with a list of Git repositories in. You run repo, it will clone them all for you. And a company called Digi do this quite nicely. So here's an example of a repo from Digi, and that works quite nicely. Oh, and when you do that, yeah, so that includes all these layers. So meta-digi, which is their BSP layer, meta-freescale, which has some stuff for the IMX chips, some demos, meta-open-embedded, because it uses some additional stuff from meta-open-embedded, Qt5, because we want to do some graphical stuff, and SW-update, because we want a software updater. So that's a good way of presenting the features of your product without putting everything into the BSP layer. Oh, final thing, yes. You can sign up for Yocto compatibility. So you can actually get the badge of approval from the Yocto developers. You can give them a copy of your BSP layer, and they're pretty nice people. They will suggest some changes maybe, but if it's perfect, they'll give you the badge. And then having done that, it would be really nice to publish the layer out. This is the thing I was trying to remember. So this is the layer index, layers.openembedded.org/layer index. So then that would appear as a BSP layer on there, and then anybody in the world can download your BSP and use your fantastic computer board. Advantages to getting it right, this is kind of obvious. Reduce development costs, help from the community. The Yocto developers are very, very keen to help people write BSPs. Happier users, more easily integrated into other people's products. So given that list, you would wonder why is it that there's a problem with BSPs? And the answer is I don't know. But the advantages of getting the BSP right are kind of overwhelming. And that is basically it. So, any questions? Or are you all so totally overwhelmed? Yeah.
So when, as a user of some hardware board, not the manufacturer of the hardware board, when would you need to make your own BSP?
So if I'm buying a board in which comes with a BSP, would I need to create my own BSP? No, not in that case. I would use the BSP that I've been given, but I may want to make some changes. So I'll need to add some bbappends because I want to use a later kernel version or some extra features or whatever. So as a user of a dev board, you will be typically modifying an existing BSP rather than writing one from scratch.
Yeah, right. So you will essentially have, like for any given hardware, there will be sort of one BSP that everyone can use because everything that's custom goes on top of a different layer.
Exactly so, yeah. So the BSP you get from the vendor, I mean, Raspberry Pi is a good example. So you get the Raspberry Pi BSP that has hooks in it for everything that Raspberry Pi can do, which is a vast number of things. And then on top of that, you just select the particular features that you want to make it into a drone or a computer or whatever you want. Yeah. Okay. Yeah. Over here first.
DTS files, are they a standard like the ones we find in a VxWorks BSP environment?
So DTS is the device tree source. It's a standard for all Linux devices. I'm not so familiar with VxWorks, but so the device tree. So device tree DTS is used throughout Linux for all architectures apart from x86. So x86, as we know, is weird, but everything else uses DTS, device trees. So you?
Just a quick comment on this one. VxWorks also uses device trees, but there are so many different functions for it. So I'd say there are about 90% equal. It's the same standard, it will look very similar, but in the end, it's just a text file. And it's up to the operating system drivers. So there are so many pieces.
Okay, so comment from the audience then is that, yeah, so VxWorks, WinRiver VxWorks also uses DTS device tree files, but they're not, they're similar to, but not identical to the Linux DTS files. Anyone else? No. Hi, yeah.
I assume this is for a more powerful embedded system, like say something like an Arduino. Would you make BSP there?
So yes, the question is, would you do this for something like an Arduino? And the answer is more or less no. So the Yocto project is mostly for Linux based systems. Not to say you can't. So you can build Zephyr. Yes, Zephyr. There is support for example, Zephyr, which is another real-time operating system. And in principle, since it's just a build system, you could do it for anything. But in practice, Yocto is mostly used for Linux. So yes, so more powerful things, 32 and 64-bit processors with quite a few 100 megabytes of RAM. Yep. Okay, question, where do you set the CPU architecture? And other things, yes. I kind of skipped over that. Yeah. So in the in the machine conf file, you will include tunings for whichever processor you're having. So you'll have include for I can't remember, ARch64 or x86 or whatever. So it's in the, excuse me, you include the appropriate machine tunings as part of your conf file. Okay. Oh, yeah, come on.
You mentioned that Yocto supports Zephyr. Zephyr comes with its own code support packages with device rules and everything. Does Yocto somehow convert that into its own format and build the final executable?
So the question is, how does Yocto fit into the Zephyr board support package? The simple answer is I have no clue, I'm afraid, because I've not used Zephyr and I'm not really familiar with the support for that. All I know is that there is a meta-Zephyr layer for Yocto, and I see commits on the mail list from time to time, but I've no real idea what it is that they do.
Use Zephyr, I use it every day.
Okay.
So I use Yocto, that's why I was curious, because Zephyr also provides a lot of these device profiles and code support packages for various codes, which support Zephyr. But I don't know how Yocto comes in and converts Zephyr.
So far as I understand, the integration with Yocto and Zephyr is exactly as with Linux. It's a bunch of BB files and meta layers and whatever that support that architecture. But the details of that, I'm afraid, are beyond me. Okay, so we're pretty much out of time. So thank you all very much for turning up and listening to me. And just before we go, there's one little thing I want to do. I hope you don't mind. I really want to do a selfie of myself standing in front of an audience, which is not a thing I've done in recent times. So shield your faces if you don't appear in my picture. There we go. Just to prove there were people in the room. So thank you all very much, and see you next year.